So we have our Miller-Rabin test. This is a test to tell if a number n is prime or composite. And to review how it works, we take each a running from 2 up to n minus 1. First we check to see if a to the n, when we mod that by n, do we get a. If that checks out, we then do a to the n minus 1 divided by 2. We mod that by n and see if we get either 1 or n minus 1. If possible, we can repeat that if we got a 1, and if we can take another square root, we do that again and see if, again, we get 1 or n minus 1. And we keep going until we can't do it anymore. So that's the Miller-Rabin test. We know that prime numbers always pass this. But the question is, do composite numbers always fail it? Or are there some composites, rare though they may be, that get through this test? It was a good sign at the end of the last video that 561, which is a Carmichael number, failed the test. Right? The Carmichael numbers passed this first part, but now that we added this second component to the test, 561 was caught. It failed the test, so we knew it was composite. And the question is, are there others, though, that still do get through even with this added level of testing? So the answer, fortunately, is no. Prime numbers always pass this test, and composite numbers always fail this test. There are no exceptions. So this is great. In fact, the composite numbers, any composite number doesn't even come close to passing this test. It can pass for some a's, it can pass both of these checks, but not for too many, for at most 1/4 of them. And that's the worst case scenario. So there aren't even any composite numbers that come really close to passing this test, like where they pass both of these for almost all the a's except one, for instance. No, that doesn't happen. Composite number will only pass a few of these, up to 1/4 at most. That's the worst. It'll fail most of them. Okay, so we have this test, and it does distinguish between primes and composites perfectly. So are we done? Well, not quite, because here's the problem. We had a test from the beginning, right? We had trial division. Trial division, only prime numbers passed the test. Composites always failed that test. The problem was, for big numbers, it took too long, right? So we have this test, and it also works, but if it also takes too long, that's not going to be very helpful. And in fact, this test does take too long. This is worse than, let me cover this up. This is worse than trial division. With trial division, we just had to check the numbers from 2 to square root of n, if you recall. In the Miller-Rabin test, we have to check more. We have to check 2 to n minus 1. And not only that, but each check is definitely more involved, right? In trial division, we just had to see if each number went into our n evenly. That's really quick. And then we have this more involved thing involving modding really large numbers raised to powers. So we've made things worse. But we're going to salvage this, and it's still going to be our go-to test, and this is how we're going to do it. The solution is, and this is the sort of real Miller-Rabin test. This is the Miller-Rabin test that is actually used. Don't do all the a's. Just do a reasonable number of randomly chosen a's. When I say reasonable number, let's say 100. That is definitely a feasible number to do. A computer can do that in just maybe a few seconds, depending on how big your number is. Even if it's really big, you can do 100 checks. What does that mean? Well, it means that we're giving up 100% absolute certitude about the result. Because if it comes back, first of all, if it fails, well, we know it's composite. But if it passes, now we're leaving the door just a tad open for a composite to get through. Maybe we just picked a composite that passes the 100 A's that we picked. But here's the thing. we said that composites can pass at most 1/4 of the A's. So if we're picking them at random, each A that we pick, a composite number would only have a 1/4 chance of passing that test. So the probability that a composite number would pass all 100 would be 1/4 times 1/4 times 1/4 times, 100 of them. So 1/4 to the 100th power. How big is that? That's about 1 in 1.6 times 10 to the 60th, which is such an enormous number that one chance in that much is essentially zero. It will never happen. It will never happen in the age of the universe. All the people ever doing Miller-Rabin test, it's just too unlikely to occur that we'll get a composite number to slip through this test. Now in math, we always prefer absolute 100% certainty, but if we can't do it without taking incredibly long amounts of time, this is actually going to be good enough. This is, for all intents and purposes, going to always catch composite numbers, right? This is just too ridiculously small of a probability of getting a false positive. So this is how we do it. And this is the state of the art in terms of primality testing. So just to show you this in action, I have some computer code that does this. And it doesn't take long. Actually, I have some extraneous things in here that you don't even necessarily need. But if I run this program, it will generate a prime number with 200 digits. What it's going to do is it's going to generate a random, I can actually just show you this part of the code. Even if you're not a programmer, you can semi-follow this. It will generate a random number of 200 digits, and then it will see if it'll run it through our test. And actually what you can see that it actually does a tiny bit of trial division first just to really seal the deal. It sees if, what this line does is it sees if the number is divisible by 2. And then it sees if the number is divisible by 3, and it sees if the number is divisible by 5. Might as well get that low-hanging fruit out of the way early. If it's divisible by 2, 3, or 5, we know it's composite. Let's not even get into the Miller-Rabin test. And we could do 7 and we could do 11. Like, we could do a few more if we wanted to, but at some point you stop that and then you go to the Miller-Rabin test. And Miller-Rabin test, where you pick 100 different randomly chosen values for A, and the code for that is up here, and it's just what I've described so far. Okay, and if it passes, then we'll get it, and it's almost definitely a prime number, right? If it fails, it's a composite number, and then it'll pick a new random number of that size and try to do it again. So it'll keep searching until it finds a prime. So I'll run this and you'll see it in real time. You'll see how long it takes to find a 200-digit prime number. Remember, with trial division, this would take multiple ages of the universe to do. So here we go. I'll hit the button, and we have to wait a couple of seconds perhaps, and there it is. So from there to there, it wraps around on a couple of lines, but that's a 200-digit number, and that is prime. We are as certain can be without being 100% certain that that is a prime number, and it took all of a couple of seconds. So that's great. Okay, so that shows that's the test, and this is how we determine if a number is prime or not.